And so I'm going to look at I'm going to define two sequences, AN and BN. Sorry, so we'll define two sequences, AN and BN. And AN will really be AN where AN is going to be BN divided by 10 to the power n minus 1. Remember that anything to, if it's 10 to the power 0, by definition, that's 1. Okay. So this here in particular means that A1 should be equal to B1. And we're going to define it like this. And we are going to define the Bn. So, and the sequences here, so there will be some properties here, is that the sequence AN is monotone. Increasing. AN are just real numbers. It's monotone increasing, and the AN is going to be defined to right. So and AN is defined like that. Sorry. And the BN are just natural numbers. Okay. So AN is defined from BN. It's really AN that we are interested in, but BN is going to be a useful tool here. And so, and it's going to be, and the BN to some extent is very simple because they're just natural numbers. So now we define Bn. So Bn is the largest natural number such that Bn squared is bigger than, less or equal to 2 times 10 to the power 2n minus 2. So that's how, right? So this here, so the sets of natural number that is bounded by that, right? That's like a finite set. So you just take the max or sup or whatever, the max of that set. Right? It's just the max of that set. So that's a natural number. Right? Okay. And now again we. Right, and then we define, so now we have the Bn's, and then again AN's. The AN are defined to be Bn divided by 10 to the n minus 1. Right. Right. And so again, you see that, and so, right, so now the first thing you observe is that if n is equal to 1, then this thing here is 0. So this means this has 1. So it's the largest natural number so that the square is less than 2. So this means that Bn, so if n equal to 1, Bn is equal to 1. And because this thing here is also 0, so this denominator is 1. So A1 is 1, B1 is 1, and A1 has to be the same as B1. And so that's also 1. Okay? So that's how it starts. And now what we want to prove is that we want to prove that the sequence AN is monotone increasing. Right? We want to prove that AN is monotone increasing. So let's just try to understand that. Right? And so again, for monotone increasing, you just need to compare 2 consecutive elements. Right? So we want to show. So this here. Remember that there's a kind of, there's ways to write a formal proof, and then there's like things you have on the scrap paper to get the idea. So this would be what we're going on the screen. Maybe the first statement is, so we want to show, this here you could certainly put as part of the proof, want to show that AN is less or equal to AN plus 1. And so this is equivalent to show that, right, so AN, since AN here is equal to BN divided by 10 to the power n minus 2, you want to prove that this thing here is less than AN plus 1, which is BN plus 1 over 10 to the n plus 1 minus 1. So this here is Bn plus 1 over 10 to the power n. That's what you want to prove. So we want to show, so you see that we want to show, so this is what we want to prove, that this thing here is less than this if you multiply by 10 to the power n on both sides. Then you get over here, and after you reduce it, you get 10, so En, so need to show that 10 Bn is less or equal to Bn plus 1. Right? That's what we need to prove. Right? And again, this just comes from that we want to prove, forget about the A now, you can just think about that we need to prove that this thing here is less than this, multiply over by 10 to the n on both sides, then there's still 10 times Bn left, and here it's just Bn plus 1. Okay, so we need to show this one here. Right, and so if I was to write it down, I would probably have some of this on scrap paper, and then I would instead sort of establish this here first, and then you say therefore, and then I'll conclude why, So, but of course that's not the way you're thinking about it, right? I mean, you first try to analyze what you have to prove, and then once you know that, then you try to write it down nicely. Okay, so we need to prove this here. And so now, right, so now the thing is that we have that, so the definition of Bn, which is right here, that's the definition of Bn, but let me copy it over here. So we know that Bn squared is less or equal to, it's the largest integer, so that you have this thing here. Right. But this means that if you're looking at 10 Bn, that's still an integer. And if you square this here, right, then this is the same as 100 times Bn squared. And so that actually has to be less than 100 times this. So this kills those, so it just becomes less or equal to 2, 10 to the 2n. Right, like that. Right? And this here you can also write as 2 to the 10 times 10 to the power 2 n plus 1 minus 2. Right? But now you see that Bn, so 10 Bn is an integer and it has this property. But Bn plus 1 was supposed to be the largest integer, so that the square here is less than 2 times 10 to 2 n plus 1 minus 2. So you see that bn plus 1 is the largest one with this property. So you conclude that, so since bn plus 1 is the largest such, and both are integers, right? and bn is an integer, then bn plus 1 must be bigger or equal to bn. Must be bigger than 10 times bn, right? Right? And that's exactly what we want to prove, right? That the bn plus 1 was bigger than bn. So we now have that the sequence an defined this slightly cryptical way, but really it's not, I mean, it sounds maybe cryptical, but it's just to, instead of using somehow digital numbers, you just multiply, you're just thinking about you want this and that many bytes. So like the n is referring to the number of digits, but including the digit that is before the point, right? So it's actually not very cryptical, but it maybe sounds a little formal here. Okay, so we have an is an increasing sequence. Okay. Now, why is an bounded, right? So, but the an is defined from the bn. So, in order to show that an is bounded, you have to figure out what is a bound for the bn, right? But you have this here. Bn is the largest such number. If I take 2 times 10 to the power n minus 1. Suppose I take this number here, right? And I square it. This is definitely an integer. I square it, then I'm getting 4 times 10 to the power 2n minus 2. Right, so this thing here, this here is the same as over here, but it's now 4. So this number here would not be allowed as a bn. In fact, it would be larger than bn, right? So this here, so bn is less than 2 to the power 10 to the n minus 1, right? So this means that an, which is equal to bn over 10 to the power n minus 1, but this is now, you see, less or equal to 2. Right? So the sequence an that we have defined is, as you would have expected, they're increasing because they really define the way they're really, if you think about it, it's really defined to take, you know, the number of digits, sort of, it's going to be like the number of digits in square root of 2, including the 1, the starting 1, right? So, and so they all are going to be less than 2, right? Okay, now let's try to, okay. So now we have that an is an increasing sequence and is bounded. So an here is convergent by the monotone. Convergence here. Right? So the an is convergent by the monotone convergence theorem. But now, if I'm looking at an squared with an squared. It's the same as an, obviously, times an, right? But an by definition was bn divided by 10 to the power n minus 1, right? And so I can write it like this, 10 to the power n minus 1. And so you see that you can write this as bn squared, and then these here combined to 2n minus 2, right? And by assumption, if you divide by this here, this thing here is less or equal to 2. So you have that an converts to a, and if you want to think about it, you think about this sequence again. And so now you know that an by this by the product rule for sequences, an times an, the sequence times itself, is converging to a squared, right? And this thing here, because each of these squares here, each of them is less or equal to 2, then the limit must be less or equal to 2. What I want to prove now is that this a that we get as a limit, that the square is in fact equal to 2. So I want to show that it's the square is, so you know, when we're doing it, this is one more proof of that square root of 2 is a real number, but this is sort of in a way how you think about it in terms of the decimals, right? And so we have the sequence an, and we have proven that it's converging to some a, and we've shown that this a here has a property that is a squared is less or equal to 2. So I want to show that that a squared is actually equal to not 1 but 2. Right? That's what I want to prove. Right? But I already proven that a squared is less or equal to 2, so enough to show that a squared is bigger or equal to 2. Right? Okay, so let's try to do that. And I'm going to use, this is going to be another illustration of the algebraic rules for sequences. So I haven't really, I here now I really, to prove that it's less or equal to 2, I didn't use fully the definition of the an, because I didn't really use that it was the largest such that an was defined in terms of bn, where bn was the largest such number. And so if I'm looking at, suppose now I'm looking at bn and I'm adding 1 and I'm squaring it, right? Well, this here cannot also be smaller than this here, because then the bn should have been this thing here. Right? So this here must actually be strictly larger than 10 to the power 2n minus 2. Okay. And so now you write, you just divide by this here on both sides. So you have bn plus 1 squared, and you divide it by 10 to the power 2n minus 2. So you know that this thing is bigger than 2. So now, but you can write this thing here, this denominator, 10 to the power 2n minus 2, you can write as 10 to the power n minus 1 times 10 to the power n minus 1. So in this way, you can split this up, and you can write it as bn plus 1 over 10 to the power n minus 1, and then times itself. This is just to make sure that it's not, it's bn, and then to the bn you're adding 1. So like that. You write it like that. But you see this thing here, this thing here, you can split the fraction up. You can write it as bn over 10 to the power n minus 1. And then you can add 1 over 10 to the power n minus 1. And then you can multiply that by itself. Right? You can write it like that. Right. But now you see, now I can write this thing here as, so now I can think about it in a slightly different way. So I have that, so I can write this thing here. This thing here is just, that is the definition of an. Right? So I can say, so what I have here is that an plus 1 over 10 to the power n minus 1 times itself, but I will just write it nicely out like this. That this thing here, remember the way it goes, that this is equal to that, which is bigger than 2. So this here is bigger than 2. Right? Now, 1 over 10 to the n. You can think about that as a sequence, right? You can think about this as a sequence. That sequence goes to 0. This here goes to a. The sum of these two sequences by the algebraic rules go to the sum of the limits. So this is a plus 0, so that's a. So this thing here goes to a. And this is the same, so this goes to a. So you see that the limit here then goes to, by the product rule for the limits, the limit here is, so you get that a squared here, and since it holds for each element, then it also holds for the limit, right? Except you have to be a little bit careful. It may not be strict inequality, but just big or equal to. And of course, in fact, it is right, equal to, because now you have established the other inequality, that a squared was bigger or equal to 2. We had already proven that a squared was less or equal to 2, so you conclude that a squared is equal to 2. If you kind of just think about it, this is really how, it sounds maybe a little bit convoluted, but it's really kind of writing down precisely what you think about when you're thinking about a square root of 2, because you think about the number of digits. And so if you take, including the first, the 1, in 1.4, including that 1, if you think about the number of digits, like the an, then the an is really defined. If you were to make it precise, you would define it in terms of this other sequence bn. Okay, so now the next thing is, so this was just like a little illustration of how the monotone convergence theorem worked. This will, play an important role next time. With yeah.
So the reason why at the top we have like strictly greater than 2, and then at the bottom we have greater or equal to, because the a's and the a squared are limits, whereas on the top we're considering each element in the sequence.
So this here, the an, this you were talking about this here, right?
Yeah.
Yep. So the an converts to a, right? This here, I think about this here, so I think about a sequence plus another sequence, right? This sequence here converts to 0, right? So the sum of these two sequences converts to 0. And likewise for this. And then I'm thinking about it as a product of this sequence with that sequence. And so, but it's like each element is in the product sequence is strictly bigger than 2, but it doesn't necessarily mean that the limit is strictly, but the limit has to be bigger than 2. right? Because they could kind of approach 2, and that's exactly what happened, of course. Yeah. Okay, so so I also just want to say that this with Lim Sup and Lim Inf, well, we didn't actually define it, but I defined, and it is how you're defining Lim Sup and Lim Inf, but we haven't talked about that concept yet. But this I talked about with that if you take a bounded sequence, then you could form 2 monotone sequences. This will play a really important role for several things. This is how one defined Lim Sup and Lim Inf. We haven't talked about those yet. It's also going to be used to prove an important theorem, really important theorem, and that I will talk about that theorem next, but we won't prove it before next time. So what is that stuff going to be used for? And how does the monotone, and what is another application? And in fact, there will be several other applications of the monotone convergence theorem. But so here's a really important concept. And so sometimes it's hard to, if it was a monotone sequence, then you could kind of write down explicitly what the limit was, right? And in all of the examples we saw so far, it was easy to write down the limits. But in general, you might not be able to write down the limits, but you want to prove that the limit exists. And so this is the following notion that then becomes really handy, and that's the notion of a Cauchy sequence. So what is a Cauchy sequence? So a Cauchy sequence, so it's a sequence with the property that for all epsilon greater than 0, there exists n, there exists a natural number n, such that if n and m are bigger than this natural number, then the 2 elements, an and am, are less than epsilon apart. So, so this is a different notion than convergence. Convergence say that that a sequence is convergent if everything kind of far out accumulates around the limit, right? This here say that and of course it will. So this here say that that a Cauchy sequence, that's a sequence so that if you are far out, then things bunch together, basically. Right? Now, of course, we will prove. So we prove on R, we will prove that the Cauchy sequence we'll prove the following. Put for still that on R, but everything is on R at the moment. That a sequence is a Cauchy sequence. If and only if it is convergent. Okay, I won't prove this now, but I'll prove this next time. And again, the proof of this involved this stuff with we defined these 2 sequences from a bounded sequence, so it would be useful there. Now, let me give you some examples. So one example, and the thing is that and we'll get to that later. But so at the moment we talk everything is in R, and then we will later generalize this, right? And so to generalize this. A lot of these concepts work much more general, and that's extremely useful, and it can be used to find solutions to differential equations. But then you have to abstract these concepts. So to where sequences are not anymore real numbers, but they are of some other space, and then you have to talk about convergence, etc. And so you can use this to define solutions to show that various differential equations have solutions. Okay, and so that often goes over using what's called the contracting mapping theorem. Mapping theorem. And the contracting mapping theorem, have all kind of forms, and but they're all, it's just a matter of what space you're looking at, and so on. But so we're looking at R here in this case, and so the contracting mapping theorem, that's a map is just a map here now from R to R, and that the map is contracting means that if you take two elements in R, so it means that T is a contracting map, if they exist. And this is really important. C is positive. I mean, that's not important. It sort of had to be positive. But the important point is that C has to be strictly less than 1. That's a crucial point. And then it has a property that when you take X and Y in R, and you're looking at how close X and Y are together, so how close that the image under T of X and Y, how close they are together, then those have to be some factor, and this is the factor, the C is the factor, and so they have to come closer. This is why C have to be strictly less than 1. Because they have to come closer. If they come closer by a factor than the original one was, then so the contracting mapping theorem say, so this is a contracting map, sorry. So a contracting map is a map from R to R, so that there exists some constant strictly less than 1, so that for all X and Y, you have that the difference between the images is this factor that is strictly less than 1 with what they were originally. And so now you get the contracting mapping theorem, and we'll talk about the proof next time. And again, this, once you know the more abstract concepts, then it's quite easy. I mean, the proof is going to be the same, etc., and it will give you existence of solutions to a lot of differential equations. So this is the contracting mapping theorem. So it says the following, that if T from R to R is a contracting map, then T has a fixed point. It has a fixed point. And this means that T of X is equal to X. And when you apply this theorem, so this is the contracting mapping. And again, it's crucial that this C is less than 1. That's what makes everything go. If it was equal to 1, you wouldn't get anything. Okay? It has to be strictly less than 1. And this thing here, if you set it up more generally, you know, if the spaces are more general than just the real numbers, then this here will be that you have a solution. It could be, it can be applied to many other things, but it could be that you have a solution to a differential equation. This statement here, you know, is like a standard application to get solutions to differential equations. And, you know, you can do use for all kinds of other stuff, okay? And so we'll talk about that next time. Maybe not we'll talk about the contracting mapping theorem. We won't talk quite yet about the applications. Any questions? Okay, great.